Ladies and gentlemen, not too long ago on this channel, we took a look at node-based data structures in Java. We saw how we could use object-oriented programming to, well, firstly build a node, and we could use this node to link out, right, to other nodes to form data structures like the linked list, the trees, and things like that. Today, we're going to go through a similar journey, but this time using C and C++. The reason why we are doing this is because C and C++ have, well, pretty interesting ways of manipulating memory that allow us to see the actual mechanics of, say, a linked list in action. All this and more in today's Random Wednesday episode. Hello and welcome back to another Random Wednesday episode. So today we're going to start off with the C version first using structs and pointers, and we're going to basically build our way up. We're going to see some issues with the C version, we're going to fix it using C++ and see what the differences are, before finally moving on again to a generic solution. Now unfortunately for this, I do require you to have a little bit of prerequisites about how C works, but the good news is, well, I've talked about all those things. Firstly, you'll need to understand memory management in C. That is, well, the whole point of using pointers, for example. So, well, we've done a video on that. We'll be using things like malloc, memory allocation. We've talked about that as well. We'll also need to understand structs, which is the episode of Friday Minis that just came out last week. So yeah, that's quite a few pieces of information you need. If you need to, go check out those videos, right? There'll be a card somewhere up on screen. I don't even know if I'm pointing to the right side here, but yeah, go check out those videos if you need to, then come back here, right? We're gonna start to apply the knowledge from all those videos into building a node structure, and from that, a linked list. So with that, let's begin. And let's start by building the simplest thing, which is our node structure. Here's the deal. Your linked list is essentially, well, a bunch of nodes pointing to each other, right? So what we're building first is our node, which holds a value, as well as a pointer to our next item. We need to be able to find the next thing, so we can essentially chain our way along. With C, it's dead simple, really. All you need is a structure that is a node, it contains the data, as well as a pointer to another node structure. That's it. The code looks something like this. And yeah, basically what you can do is you can chain along a few of these items. As you can see, I've created 3 items starting from the last one. The third item points to nothing, but the second item points to the third, and the first item points to the second. This is essentially a very simple linked list. Since the items are linked to each other, I can simply request for the next of an item to move forward. So asking for the next of the first item gives me the second, asking for the next of the second item gets me the third. That's the idea. What we've just done is we've just built our node and then manually linked our nodes together. And that's great. However, 2 shortcomings come to mind immediately. Firstly, we are just building our nodes as variables, so they live only within our main function. Clearly, the more dynamic way would be to use malloc, so, well, our nodes actually hang around. Second, right now we are directly manipulating our node connections, and while that's fine, providing an additional level of abstraction, in other words, actually building a linked list data structure, will make it easier for us to manipulate the contents of that list. So, well, let's build a full-fledged linked list data structure, and we'll see how things work. Now, in the case of C, we can only build them as functions and call them. So, well, let's do that. Now, before I enter into the actual explanation of a linked list, do note that we have talked about linked lists multiple times, right? We did this the last time we looked at node-based data structures. So as usual, I'm not going to go into too much detail. Now, what I'm going to do is I'm going to switch into my code page here, right? Essentially, these are the main things we're going to cover. We will briefly touch upon the theory as and when we need to, but I'll try to keep things short. Firstly, before we jump into the linked list stuff, do take note, of course, of our setup. Of course, we need to have our node struct, right? And since this is C, we have no other way of keeping track of the head of our linked list except by using a global variable like this. Well, there are ways, but to keep things simple, we'll just do it this way, right? And we're going to implement everything else as just a function within the page itself. And we'll have a main function, right, to set things up and to drive everything. So that's what's going to happen in a nutshell. Let us now take a look at the actual logic. For this, let's start with a find or get function. Now, in my code, I call this get, but the idea is if you're going to find, a particular element, here's how you do it. Essentially, you're going to have to create a current pointer, and it is going to have to move its way through the list starting from the head to find the item you want. Let's say I'm looking for item number 2. How I'm going to have to do this is I'm going to have to put current at the head, maintain a count which is set to 0, and then run a loop. Each time, if the count is not yet correct, the current is updated to the next of the current node, and essentially what happens is this pointer moves forward like so. Of course, we don't just move it forward, we'll also have to update the count as we go along. So the idea is we keep doing this until we end up at the element we are looking for. Let's take a look at the code for this part. Essentially, the code looks something like this. Very simple. We create our current, right? This is a pointer of type node, and it starts off at the head. Now head is also a pointer, so we simply, copy the pointer value. We have a for loop here which does the counting for us, right? Our count is represented here as the value I, and the idea is the user will supply a position. You'll keep counting forwards until you hit that position, and all you do moving forwards is you simply update current. Current points at a node right now, go to that node, find its next item, and set that onto current. When you do that, current moves forwards. That's it. Now let's move on to insertion. Let's say we wanted to insert a new item over here, right between these two nodes. Our approach would be to, use our get function, right, find our way to the slot before, right? So this is the previous item, the one right before where we actually want to perform our insertion. And in order to actually find this, we'll have to, get the actual position we want to go to -1, right? You'll see that in the code later. Basically, you've got to find a node that will come right before this new item. What you're going to do to it then is you're going to have to find out what is its next item, because now that would be the next item of our new node, like so. So the new node must point to it. Once we have that reference, our previous item simply points towards the new item. As you can see, this essentially sort of flattens out to the correct structure, right, with the correct order. Again, let's see this in our code. Of course, we'll need to take in two values, right, not just the position, but also the value we want to actually store. We'll create our new node by performing a malloc operation. We're actually allocating memory here, and that memory is the size of a single node. We then want to populate the two values, right? We'll put in the actual value that the user wants, and we'll set the next pointer to nothing for now. There are actually two cases for insertion, one of which we didn't go through just now, and that is if the node is going to go to the head of the linked list, we simply update the head, and the next item that a new node has to point at would just be the current head. Otherwise, if it's not at the head, then we'll do the same algorithm we've just looked at. Go to the previous item, see we had to get position -1 because that is the previous, right? So we get that item, and the idea is the new node must point to the item that comes after. Meanwhile, the previous item must point to new node, right? These two manipulations, and you get the new item in place. Then we have deletion, which works again on a very similar principle. You have to find the previous item once again, and the idea is you have to find the item that comes after the item you want to delete. Once you have that, it's simply a matter of taking the previous item and pointing it to that item. The idea is that the item you want to delete now becomes out of reach. Going back to our code, here is how we would do it, right? You give it the position. If it is the first item, we simply point the head to the item that comes after the current head. In this case, since we're dealing with memory we've allocated ourselves, we have to be very careful to not lose track of that piece of memory. We free it now while we have the ability to find it. we can't free this later because we have no way of getting ourselves to that node. So this is very important. If you don't do this right, you get a memory leak, and that would be a problem. This is the case of the head. If you're not deleting the head, you want to, again, find your way down to the previous, find the item you want to delete, right, which comes after the previous. And the idea is, again, the previous item will point to the item that comes after what you want to delete. Similarly, you must free up the memory. Now, speaking of freeing up memory, we do actually need to do one extra thing that we didn't have to do in the Java version, which is to properly free up everything. When you're done using your linked list, well, since you've allocated that memory, it's your responsibility to get rid of it. So, we essentially traverse through the entire list once, visit every element, and free it up. Do note that I'm using quite a roundabout approach to do that here, and the reason is because, well, you have to be careful not to delete a node until you've found the node that comes after. That means you must be able to call current arrow next to find the next item before you actually free up the actual node itself. That's why I've created a previous here, right? And the idea is that I still have some way of finding my item even after I've moved forwards, so I can free it up. For convenience sake, I also have a display function, right? All it shows me is the address and the value of each item while traversing through the entire list. So now we can come down to our main function, right? The idea is I start off initializing the head to nothing, inserting a couple of items, and then taking a look. After that, I'll try my deletion and take a look again before properly clearing out the entire list. As you can see, the results are as you would expect. The first 4 insertions insert 1, 2, 3, and 4 at the back of the list, while 5 and 6 come in front. So, well, our first set of results are, correct, right? And then after this, we delete first the head and an item in the middle. And that leaves us with 4 items, still in the same order. And there you go. That will be your most basic node-based data structure in the C programming language. Now, we have one tiny little drawback here, and that is the fact that, well, these are just functions that are lying around. But what if we wanted to consolidate these things together to have a nice single unit of computation that we could work with? Well, let's use classes. And in order to use classes, we're going to have to switch programming languages. C doesn't do classes. C++ does. So let's give that a try. Firstly, before we go into classes, we're going to just port our entire code to C++. Now, while C and C++ are very similar, in this case, we're playing around with memory, and as it turns out, some things look a little bit different when we do that. So first, let's explore the differences before we actually step up our code. What we have here are the 2 pieces of code side by side. The C code is on the left, the C++ code on the right. And as you will see, the differences are subtle. I've tried to line up these 2 pieces of code as perfectly as I can, but yeah, let's take a look at the main differences. You'll see one right here with the insert statements, which I'll highlight on both sides. Now, in C, we would use malloc to allocate memory. In C++, instead of saying malloc, we would say new. That's just a subtle difference between each one of these languages. Now, malloc still works in C++, but it's no longer the official way. New is now an actual keyword within the language itself, and, well, that means that's the better way of doing things. In addition, this one is a little bit more subtle, but in C++, the way you construct a struct is slightly different from how you do it in C. Essentially, your struct becomes a function, or to get a little bit ahead of ourselves, it kind of acts like a class. So just note that there is a slight difference in terms of how you actually build new items. At the end of the day, however, the way we use this is exactly the same. We get a pointer to it, and we can start assigning values to it. Let's move down a little on both these pieces of code and we'll see another difference. Just like with malloc, we no longer say free. Now we say delete. So yeah, again, we're making use of new vocabulary given by C++. Also note that because this is called delete, I can no longer call the function name delete as well, right, there will be some kind of a conflict there. So instead, I've renamed this to delete node. This of course applies throughout any function that, does freeing up of memory. We now call delete instead of free as well under the destroy function. Another thing I did instead of using printf, right, which is what we have to do as a standard for C, I can now just say cout. Of course, printf still works just fine, but, well, since we're moving to C++, let's just move everything accordingly. So yeah, apart from the preprocessor statements at the, very top of the piece of code, those are the changes, right? We are still doing structs at the present moment. And yeah, from C to C++, we get the exact same set of results. That means our porting operation has been successful. Now that we have these things out of the way, we can start to convert our code, from structs and functions, which are separate things, to a single class, which brings everything together. Let's see how things change when we do that. Now, right off the bat, we've changed two things in the classes. We have a node class, as well as a linked list class. Now, for the most part, at least under the linked list class, things look the same. The node class seems a lot more complex, in comparison to its struct counterpart, but it really isn't. This is what we have in common with the struct. Ultimately, your node must hold these two pieces of information, right? So that's never going to change. However, we now have a bunch of other things, right? This, as well as the private flag. The idea is that, these private attributes cannot be changed directly from outside this class, that's all. So we need to add these functions to allow these values to be manipulated. These are essentially what we call getters and setters, also known as accessors and mutators, right? So the idea is that we have functions like these to get either the pointer value or the value within the node itself. And these are there for you to actually change those values. So this allows you to set the pointer to the next item. This allows you to set the value. Finally, our last function here is called the constructor. Now, for the first time, what we can do is we can run a function, and that gives you back a node. That constructs a node, to use the OOP terminology. You don't have to create a constructor. C++ knows how to construct things by default. However, if you wanted to do something special during the construction process, this is where you specify it. And what we are doing now is we are taking this opportunity to initialize the values. When the user creates a node, they'll have to give us the value, and that is the value that is being stored inside our node. At the same time, the next pointer is automatically set to nothing. So yeah, with this constructor, what happens is we know exactly what's inside the node from the moment it is created, and that is always nice. This is our node in a nutshell, and once we're done with this, we can move on to look at our linked list class. Like I said, most things are the same. In this case, our head object is now held within the linked list itself. This of course makes sense, right? Every linked list needs to have its own head, so that we can use that to find the rest of the contents held within the linked list. The first function we see here is a constructor, and all it does is it sets the head to nothing. Again, it's there for us to, ensure that we have a clear starting state. What you'll find is that everything else looks basically exactly the same. The only difference is that when we're trying to get information, for example, we can no longer just, refer to the value held within the node. We have to call the corresponding function. This again is the result of having things private within the node class, right? So again, we have to use the getters and setters to, touch the actual values. Aside from that, things are exactly the same. Our logic is exactly as it is, things haven't changed. It's just that now we have to again express things using slightly different vocabulary. Notice here that in our insert function, we are now making use of our fancy new constructor for the node class. Notice previously, we had to add 2 more lines here to set the value and the next pointer. And we no longer have to do that now, thanks to the fact that we have a nice constructor doing it for us. Don't forget, we still have the new keyword here, and that means memory is being allocated. So yeah, insert, delete, right, exactly the same as well, except we change things to, make use of the functions instead. Same deal for display. Now, another thing that's different here is this function. Notice we've replaced our destroy function with this, a destructor. If you can construct a class, of course it makes sense that you can destruct it, right? You can get rid of it when you're done with it. That is essentially what this function is for. Notice how similar to the constructor you make use of the name of the class, but instead we write a little tilde sign before it. The purpose of a destructor is simply instructions on how to clean up. When I'm done using this class and I want to say, hey, throw this away, what logic do I need to go through to make sure that everything is actually being deleted correctly? Of course, that's exactly what we were doing before with the destroy function. So, well, this just comes in handy, right? Turns out there is a nice mechanic for this already in object-oriented programming, so we just make use of it. With this, we have both our classes ready and we can start to use it. Over here, in our main function, things are mostly the same. Now, we create the linked list where we construct it based on our class. And yeah, in the future, whatever operations we run, we have to run on our linked list object. So the name of this linked list is simply LL, right? And what I can do is I can do my insertion, display, and all that, as usual. Now, notice one subtle change, and that is the fact that I no longer have to destroy the linked list. I didn't miss this out, I didn't forget this. As it turns out, C++ actually destroys whatever objects you've created for you when your program terminates. So that's one less thing you have to worry about. C++ can clean up after you, and how it does it again is by calling the destructor function. So yeah, that's one less thing to worry about. We now have everything in place, and if we run it, you'll see that the results are exactly the same. This tells you that our linked list, the class version, is now working as we expect. Ladies and gentlemen, we now have a linked list data structure that is in a class form. With this, it's now so convenient, right? Because we can have a linked list, it can do its thing, we can build a different linked list that will do its thing. And yeah, both of these are dynamic data structures. So it's very, very powerful, a lot more powerful than your basic array. Now, we have just one more problem to address, and that is right now, our linked lists only hold integers. The way we dealt with this when we first built this in Java was to use Java generics. Right, generics is a way to say that, well, this type is able to contain an unknown type or a variable type t. We can assign the type, and well, moving forward, that data structure works with that type. Well, C++ has something similar as well, though, well, expressing it isn't as pretty as it is in Java, though it is quite similar. Let's see how we can tweak up our code, right, and then let's test this with a different data structure. How you do so-called generics in C++ is by using this thing called a template class. The idea is we want to build a class, but we haven't decided what type it is just yet. So for now, we'll call it T, and later on when we actually, construct an object of this class, C++ builds the correct version of the class that supports this template type. So here's essentially what we need to do. Before building our class, we have to say that this is a template class and it's going to work with the type T. So you can see that we've basically replaced every instance of integer with T, right? So essentially this is our node, and instead of storing an integer, it now stores the type T. When you try to get value, it takes back the type T. When you try to set, you're setting type T. So everything is now with respect to this variable type. This makes our node versatile, so we can store basically anything we like inside it. The same needs to be done for the linked list. Again, we say template class T, right? And yeah, everything inside now works with T. Now, as you can see over here, what happens is we are trying to build a node, right? So for the first time, we're talking about this template class as a user of it. But in this case, we're simply saying, well, we want to use type T, right? It is the unknown for this class that I'm passing over to that class, the node class up there. So yeah, I think you get the idea, right? Every time we talk about node, we have to be clear that it is a node of type T. So yeah, whether we are just talking about a type or whether we are trying to instantiate like we are doing here, we have to mention T. Anytime we mention node, we have to basically link it with its correct type. Everything else works basically the same way. When you do insert, you are now inserting objects of type T, right? So same deal for deletion, right? We mention T as much as we need to. Same deal for display. Same deal for our destructor. Anytime we mention node, we must mention the type. So we can now go down and actually use this. In this case, instead of using integers, I'm going to be using characters. So I tell C++ that I want to store characters in my linked list, and yeah, I create my linked list like so. So what happens is this character type is going to bubble its way down into the linked list and, as a result of that, to the nodes as well. And what that means now is I can insert characters into my linked list. If I switched out the type over here, I'll be able to store a different kind of information. At the end of the day, however, how things work is exactly the same, right? I'm just storing a different kind of information. So yeah, there you go. What we call generics in Java is what we call templates here in C++, but the idea remains the same. We now have a versatile type of linked list that can hold any type of information. And there you have it. That was, building our node-based data structure, turning it into a linked list, and then from there, seeing how we could first package it as a class, and then as a generic class. We've basically looked at C and C++ in the same video, but most of the contents were fairly similar, so I hope that wasn't, too much of an information overload. But yeah, there you go, right? And you can extend the same idea to do a bunch of other things. For example, you could build a binary tree, right? And to do that, you would basically tweak up your node so that it will, instead of having just one connection, one pointer, it would have two. Of course, you can augment this further, add another pointer so it can find its way back to its parent if you want. What about a general tree? I've seen a pretty interesting one in which you could build a general tree with just two nodes. Essentially, you would turn a tree that looks like this to a tree that looks like this. Every node gives you two things. Firstly, a way to find, its child node, its first child node, as well as a way to find its sibling, the next sibling, in that level. So it's not the prettiest of ways, but at the same time, it works, it gets the job done, right? You just have to tweak up your functions so that, it deals with things correctly. But anyway, that essentially is it for this episode on node-based data structures, this time in C and C++. Hopefully this has been an interesting journey, right? Playing around with pointers and things like that is always fun. As long as you have the right idea of what's going on. But yeah, that is basically it for this particular episode. Thank you very much for watching, and until next time, you're watching 0612TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.